Hey everyone, welcome back to another session. The weeks are flying by, so let's go and see what we can do today. We're doing two things. We're looking at chapter 11, a quick overview from last week, and then looking at sampling chapter 14. So let's dive in. As always, you can break this into different sections if you like. You might want to stop halfway through, have a break, cup of tea, and take it from there. Do a few push-ups. It's always good. So we said last week, really, we want to gather. The importance of gathering data correctly is going to help us make some decisions for the future. So looking ahead at what our needs might be, whether it's a business or whether it's a government, and we've got some big projects we need to plan for: hospitals, roads, railways, schools, whatever we'll be needing, and businesses. Should we open a supermarket in this brand new subdivision? Is there a population and an income to support that? So before we throw $5 million into a project, we want to make sure that there's a reasonable grounds and reasonable chance of success. And statistics is all about, I guess, minimizing the risk, maximizing the potential or the success options we have. We talked briefly about the difference between the population and the sample, and we said that the population didn't need to be huge. We said the population could be, if I gather all of the data in a particular class, then that's the population. It's only when I just, my class is big, I've got a class of 400, say, and I just gather the data for 40 students and try to make an estimate about the rest of the class based on that sample, then we have a sample. Some people think population has to be huge. Doesn't necessarily need to be that big. And we also talked about the difference between a parameter and a statistic. Parameter is any statistical measure of the population, and we identify whenever you see a symbol like mu, the Greek letters, or sigma for the standard deviation, mu for the mean, you know we're talking about the population there. Whereas a statistic is a descriptive measure of a sample, and so not just the statistics, the subject, but statistic, the measure of a sample. And Roman letters such as S for the standard deviation, or X with a little bar across the top of it for the mean of the sample. So we'll just zip through these. The calculator, if you're using the financial calculator, gives you a hint as well. The Y with the bar above it, the mean of the second set of data we enter in. And if we went recall 4 because it's green, we would get the mean of the first set of data that we'd entered. SX, standard deviation of the sample. Sigma X, standard deviation of the population. And we said last week, one way to remember it is the sample is smaller than the population, 5 is smaller than 6, and that's another way of helping you identify, hey, is this the sample standard deviation or the population standard deviation? We'll be doing these calculations in a week or two. And we also said descriptive statistics is just us gathering the data and describing what's happened. A statistical inference then is when we use the descriptive statistics to try to do, potentially look into the future, and based on this historical data that we've gathered, try and make some predictions about the future, and also possibly try and make some inference about the rest of the population. Very quickly, primary data that we've gathered ourselves from our own survey or own techniques, however we've gathered that data. Secondary data is somebody else has gathered the data on our behalf. And we saw last week that the Australian Bureau of Statistics has a plethora, lots of data gathered for us. And go back and look at that if you need to refresh. And we also spent a bit of time just looking at the difference between quantitative data and qualitative data. And quantitative data, measuring values or counting, expressing that as numbers, whereas quantitative data is something about the character or quality. Oops, where is it? That is still quantitative data. Maybe it's on the next page. Well, let's have a look. Quantitative data, passengers in a plane, sales, profit over time, number of patients, all of these we can quantify. Qualitative is a measure of the quality, if you like, of the data. So some sort of characteristic of the data, colour of cars in a parking lot, the grades of students in a classroom, types of, coins in a jar, shapes of biscuits, all those sorts of things, qualitative data. Here is some more slide straight from Google. And I don't know if it's telling us much more. Just suggesting it's a little harder to do statistical analysis, but you can graph qualitative data. I think that's on the next slide. Almost. A little more. So this is all qualitative data. Smells, colours, names, suburbs perhaps. Quantitative data, scores, weight, shoe size. Measure it, count it, or measure it. And here we are. Can you graph qualitative data? And the answer is yes. These are all qualities, colours, and we're graphing it. Get a bit of a sense of the range of the quality in our data. Well, moving on to chapter 11, we started to group data together. These were, we had 50 pieces of data of unemployment, and just as raw data starts to look a little bit confusing, to try and make sense of it, we arrange it from lowest to highest and group it, and that starts to give us some sort of a sense of meaning to the data. And we also said, if you get this little bracket here, that's telling us that if you had 4, this is 3.75, anything from 3.75 up to and including 4. The square bracket, we said, sort of looks like an I, includes up to 4. And 4.001, say, for example, would go into this grouping here. And the midpoint's helpful for us in calculating the, doing a whole lot of statistical analysis. The reason we use the midpoint is, for example, when we've gathered the data like this, of those 16 items that was somewhere between 4.25 and 4.5, how many of them were they closer to 4.5, closer to 4.25? Where were they? And we make the assumption that, look, let's use the midpoint as an indicative value of this particular class interval. So that's the reason, finding the midpoint, find the beginning value and the ending point and divide by 2, and we'll use that when we're doing our calculations. Looked very briefly at the cumulative distribution. 1 plus 5 is 6, plus 16 is 22. If we do it all correctly, the total down here will equal the total of the frequencies. And helpful for drawing an ogive, which we'll see in a moment. It's important for us when we're doing graphs, a few basic rules that will help the graph make sense and make it work. Make sure it's got a title, make sure the axes are labeled so you know what you're talking, people can see at a glance what you're trying to achieve, what you're trying to measure. Try not to make too many curves on the same graph. We'll see a bad example, and we saw one last week. We'll quickly go over that. Quote your sources, and it's not always a blind rule that you go to 0. There are times when you might not want to go to 0, but where possible, if it makes sense, go to 0. So here we are with a histogram, and last week in class we spent a bit of time drawing one of these in Excel, bar graph, and all the bars are joined together. Frequency polygon is just the joining of each of the middle of those bars on the previous slide. So if I was to draw a polygon here, bang, bang, up to the middle, down, etc. There's my frequency polygon. And an ogive. we said was helpful for trying to work out best way to interpret an ogive is we know the total number of months were 50, and if you're trying to work out where's the bottom 10%, where's the top 20%, whatever. Imagine you said, well, where's the midpoint? So 50, half of 50 is 25. Half the months had unemployment rates less than 4.75 and half greater than 4.75. Just helpful for reading and interpreting the graph and making sense of it. Pie chart. This is a pie chart in a snowstorm. Fact, it's on the next slide. And you've probably drawn some pie charts in the past. Excel does a good job. Just highlight the data and select pie chart. And you can select, hey, do you want labels? I always think it's a good idea to put labels on your pie chart. It makes it easy to spot instead of somebody having to guess that China's exports were, 31, or exports to China were 31% of the total. A Pareto chart we said was helpful for particularly if you're in the service industry and you're trying to fix the major problems first. Let's find out what the number one issue that customers were having, or the number one default we've got to try and look into, and then in order of let's try and go on to this one next and this and sort it out that way. So helpful to rank data from the greatest to the least. Scatter plot. It comes into play in the next few weeks when we look at the correlation between what's happening in our X series of data and our Y series of data. Can we see a pattern? Bit of a pattern here, bit rough. The closer those dots are to the line, the closer the correlation between this and this event over here. And this is why one of the rules said, we had a brief look at this last week, one of the rules, why it said you should go to 0 is that if you don't go to 0, you could mislead people. They could look at that and say, wow, look at us compared to the competition. And yet this is the real picture. It doesn't look as flash. It's exactly the same data. And possibly, though, there are times when going to 0 isn't that flash. You might say, yeah, I'm losing the sense of what's going on. I want to see the fluctuations. So all we've got to do is condense our scale. And this is exactly the same data, exactly the same graph. And we can start to get more of a picture of the fluctuations. And we, as I said, we're losing it a little bit up here. So there are times when, there are times when we might need to be alarmed and might want this graph to see trends and predict trends. And finishing up on this, we said last week that this wasn't a bad graph because of all of the labels on the lines going across. It's helping us to read it, and it's identifying different events that are causing. We tried to look into some of the peaks and troughs to work out what were causing these changes. And we said this is a bad graph. Classic example of way too many curves on the one graph. You just lose it. Very, very difficult to interpret. Okay, so that'll do us for our revision on chapter 11. We're moving into sampling now, and just got to find where that is hiding. Might have to just shut this down. Just bear with me while we do that. Not sure why it's doing that to me. I had it hidden. I had it just behind. Might be a good time for me then to if I can't get it in a second, stop presenting. That sounds like a good idea. I did have it. It was here. I'll just have to open it. Just one moment. Chapter 14. It was on the screen a moment ago. Okay. I just want to make sure that the screen is still being shared. So, okay, we are sharing. Okay, so you're seeing what I'm seeing, which is good. And I'll just shut that down for a moment. So sampling. And it's not going forward. There it is. So visual presentation of data first, and then we'll get into sampling. Look, here they've whacked a coin in. We're trying to graph, what are we? Exchange rates or the Australian dollar's performance. And it was published in the Sydney Morning Herald. And I guess what they're trying to do is draw your attention to it. People are attracted to cash, maybe. And maybe this picture here is meant to force people to stop what they're doing and pay attention to the graph. Perhaps that's the reason for that picture. So a picture paints 1,000 words, but less is more, perhaps. There's a lot going on here. And do sometimes too many pictures detract from what you're really trying to present? I'll leave that for you to decide, but they really wanted to get our attention. I get that we're talking about music and CD sales, but anyway, there it is. You decide. We saw last week how a really good presentation puts things into perspective. So we've got time down here on this axis, and we've got pandemics through history, and it's starting to put things into perspective as to where we might be: SARS, Ebola, swine flu, and COVID. And another example of the death toll and dates. So it's quite a handy. Your mind can capture the severity of these different events through history. The histogram, did a bit of that last week. That's fine, but essentially, hey, from 0 to 20, got a graph 13. 0 to 20, there it is at 13. And just keep going and graphing it. What a wonderful graph this one is. It's breaking all the rules. There's no title. I guess you could call comfort zone a title, whatever comfort zone means. It's all brand X pain reliever, can assist in relieving a headache. It's the advertising gurus trying to make us think that their product is scientifically proven. There is no scale. There is no access. Well, we've got time. We've got time. And possibly, we've got brand X, or so this is their brand and this is other brands, and look at us. It means nothing. You knew that. Which graph is more appropriate? Again, this is the one that goes to 0, and this is the one that's not. And there are times when possibly this is what you're after. You're losing a bit of the scope of things, perhaps, when you go to 0. So it doesn't necessarily mean this is wrong, although this does put it a little more. This makes us look like we're growing retail sales. Look at our sales. Look at us go. Wow, fantastic. This perhaps puts it in the right perspective. Maybe it's not as spectacular as we really think. So sampling. Why would we sample? It makes sense. We're going to save some money and time rather than have to gather all the data from the entire population. And if it's all about quality control, then clearly, when we quality test the Samsung phone and drop it out of the 3-story window, if we did that to all of our product, we'd have nothing left to sell. So we take a sample and try and draw a conclusion about how the rest of the product might perform. And sometimes it's just impossible to gather the whole information for the population. Why might we take a census? And it's because we don't want to risk the chance that we'll make a mistake in our sample, and our sample may not be representative of the population. It's the one true way of when we've gathered all the data, and if we've done it correctly, then we can rely a lot more on that data. Well, what's a random sample all about? And is it really random sample? They call it random breath testing, RBT. But whenever there's some judgment there, is it really random? On the side of the road, it's possible that our police officers might be interested in targeting P-platers, or they see a hot rod come through and they think, it's interesting. So they may well be, just without even thinking about it, making a judgment on who they pull over, even though they might be trained to say, make it random. That you can't help our our human nature will come into play. So a good sample should be unbiased. It should be representative of the population. So what are some of the rules? Try to choose a sample that is representative. Just don't go for the easy option. And I'll talk about some times when sometimes that might happen. Yeah, I'll go for it now. I'll talk about it before I forget. Early on when I was auditing, we're at a client's place and we had to sample some invoices that were tucked away in a cardboard box up in the attic. It was summer. It was really hot up there and dusty. And again, you think, I'm just going to grab the closest thing. I'm just going to get in and get out. So it was a classic case of our sample possibly not being that random. It was just, let's grab the closest thing to the door. And so our audit sample was possibly not quite that random. And also another good time for a sample, imagine you've got this truck driver and you're trying to verify that the delivered 10,000 bags of potatoes. You do not have time to count or weigh 10,000 bags of potatoes, so you might just take a quick sample and sign off on it. You're certainly not going to keep the truck driver waiting for 3 hours while you sample it. There are times when your sampling frame may be bigger, so an over-registration might be, in this example here, maybe we are trying to, our sample needs to be where our population we're observing is all female members that are members of the Chamber of Commerce, say. So if we go through the entire Chamber of Commerce membership directory, we've got more than we need. Sure, we've got the male members there. So we've got over-registration. If our aim was to, we're trying to gather data for the entire population of female business executives, say, and we're only using the Chamber of Commerce to draw our sample from, well, we've got under-registration because there will be, female business operators that are not in the Chamber of Commerce. So it is important, wherever possible, make sure where you're gathering the data from does in fact include the entire population that you're looking at. So random sample should technically be random, and every unit of the population has an equal chance of being selected. So not also known as probability sampling. Excel has a random number function which will enable you to gather some random numbers. I'll show you there are some random number tables in your textbook. We'll have a quick look at them in a moment to show how you might select a random sample. But any other sort of sampling, judgment sampling, where it just won't, there'll be some judgment involved, it won't be random. So convenience, snowball, you can read up on these. Sometimes these types of samples become exam fodder or assessment fodder for questions, so it is worthwhile knowing, some of these terms. We're going to look today just at stratified sampling, perhaps, and systematic sampling, but have a look at some of the others. Snowball, snowball is all about, we're doing a survey, and at the end of the survey we say, oh, by the way, could you recommend somebody else that might be interested in our product? And so you're snowballing off, you're rolling off the previous client to pick up your next sample. It's certainly not going to be, it's not going to be a random sample. It's drawing you to, a particular type of person. Simple random sample. Let's have a look at it. So imagine we want to find we've got 30 clients now, real estate. 30 clients on our books, and we want to find a random sample of 6 of them. So we go to our random number table. There are no rules as to how you work with your random number table, but we know that the number of clients are between 1 and 30. So We might choose to start at the top left-hand corner. We don't have to. We could start here if we wanted to. But let's imagine we started here and we start going. We say, well, 99 is too big. It's not going to fit. 43 is too big. That's our samples, 0 to 30. 78, too big. 79, too big. 61, too big. 45, 73, 73, 75, 52, all outside our clients that are numbered 0 to 30. Oops, I've lost my mouse. 97, 96, 93, 90, 94, 34, just outside our sample. 47, 53, and there's the first one. 16. Okay, we'll pick up 16. Looks like the next one's 18. Pick that one up. 50 too big. 65 too big. 60. 1. Let's pick that one up. 27's in the range. Keep going, and we just keep going down until we find our, and stop when we've found our 6. And we end up with these dudes. That is based on what we did. Notice the notation: big N, population, little n, sample. And there is our random sample of 6 clients that we're going to look into, and try and then, based on what we find with those, we'll draw some sort of conclusion about how the rest of our clients or customers or companies might be feeling. So no rules. We'll look at one more example. Oh dear, I've got the wrong slide. Yeah, okay. I'm just going to have to wing it for a moment here. Imagine I've got, I want to find my customers. I want to find 50 customers, and my customer numbers are between 0 and 1,000. So 0 and 999. So I've got 3 digits I'm looking at. And the idea is there are no rules. Imagine I decided to start here. Right at that point there. I can go up, I can go right, I can go left. I've decided to go down. So I start looking, and I pick my first. So my first number I pick is 364. I go down 610. That's in the range. 548, 147, 037. The 30 client number 37. Client number 888, 826. I just keep going, and these are all totally random. You can see they're jumping all over the place, and I stop once I've picked up my 50 items. So because of that, I'm going to just have to skip a few slides because it's giving me, I tried to summarize it to keep these videos short. The stratified random sample, you might have driven along a road where there's a cutting and you see layers. You see the sediments. You might have heard about that in geology when you were doing science at school. And that's the same sort of thing, these stratas that you see, these layers that might happen in a sample. So if I'm sampling accounting students and 80% of the population are female, I want 80% of my sample to be female as well, so it's representative of the rest of the population. And so a way to calculate that, again, there's my population: 5,000 adults, 2,800 females, 2,200 males. And I'm taking a sample of 200 adults. How many females should I take? 2,800 over 5,000 times 200. I need my sample to have 112 females. Do the same for the males. 2,200 over the total times 200. I need to pick up 88 males, and I'll have the right proportions, the right stratas for my sample. There might be times when, imagine we're a radio station and we separate our sample or our survey into different age brackets, and we try and work out what our target audience is. And we might be particularly interested in the music tastes of people in our audience in this age bracket and also this age bracket, and compare them, see what the similarities are, see what the differences are. And potentially, if we wanted to target both, if we wanted to get a larger audience, we might pick the music styles that seems to match for both of them, and we might be able to cater for the 20 to the 50-year-olds potentially. So thus the reason, and there are times when you definitely want to gather all of the data and focus on the data that you're gathering here. This is my target audience, so let's make sure we don't play this stuff, let's play this stuff. Systematic sampling, quick look at that is, and in fact, it's better to go to an example to make it work. So imagine we want to sample 150 invoices, little n sample, from population of 500, big N. And therefore, we go grab our population, divide by the sample size, 3.33. So we'll round it down perhaps to 3. And what we're going to do, it's still a random sample, but it's systematic. So check what happens here. We go, look, I'm going to take every third item, every third invoice number, but where do I start? Do I start at invoice number 1, invoice number 2, or invoice number 3? And at random, I say, let's pick number 2. There's my starting point. And then from there on in, I just keep this, I add 3. And I go, let's pick the 2nd, let's add 3. I'm going to pick the 5th, let's add 3. I'm going to pick the 8th and the 11th and the 14th and we just keep going and stop when I get close to 500. And I'll have my 150. Cluster sampling, very briefly, you could read about all of this. I won't talk too much about it, but it is just where you put things in a little cluster, and it works for geographic locations. So I'll go back for a moment. So instead of you having to drive over the whole country, perhaps you could take a sample of a particular suburb and assume that that's representative of other suburbs. If you think of Sydney, though, we do have a different population in the different regions and suburbs of Sydney. So, is it really going to be representative of the rest of the population? And I'm going to let you read up on those. Won't talk too much about those. You can read on them fairly well. We might just quickly touch on this. This is sometimes it's good for us to know the distinction between what's a sampling error and what's a non-sampling error. And pretty easy to identify. A sampling error is any time when our sample is not representative of the population. So anything that causes there's some difference between our sample measure, our statistic, to be different than it's a misrepresentation of the rest of the population. And a non-sampling error is any other potential error that could occur other than sampling errors. So you've misrecorded data, it's a vague, you've got a survey question that's really vague and people, it's just not clear and they give a bad answer. So all those sorts of things when people don't tell the truth when they're being surveyed, or overstate their answers. So all those sorts of errors can creep in, and so there's the distinction between a sampling error and a non-sampling error. So make sure you're comfortable with that. And so it's an ongoing process, perhaps. We select a random sample, we calculate the mean, perhaps the statistic is our measure, our mean measure of the sample, and based on that, we try and the process of inferential statistics, we try and infer what the population mean might be once we've calculated the sample mean, and we draw some conclusions about the population, and we just keep going. If we want to continue the investigation, select another sample and prove our figures, or in the future years, over time, the population, we might think it's changed. So let's take another sample and revisit the sampling techniques. Yeah, we'll touch on these elements in class. The last thing we might think about is how big should our sample be. So these will be some formulas. You won't have to commit them to memory. They'll be given to you, accessed for any of the assessment items you might do. But we've got this little formula. If we wanted to be 90% confident of our sample, or that our population proportion is indicative of our sample is indicative of the population, we'll use this factor of 1.645, which will make more sense when we come to do the normal distribution in a few weeks' time. And 95% will use this 1.96 figure, and 99% 2.58. And we'll divide it by 2 times whatever we are prepared for our estimate of error, if you like, to be? How far out are we going to be? So let's make it work. So imagine we'd like our estimate to be within 5% of the true proportion when we want it to be 95% confident. How large should our sample be? We just plug the data into the equation. So our sample size should be greater than or equal to 1.96 divided by 2 times 0.05, which is 0.10. Remember to do what's in the brackets first. 1.96 divided by 0.10 equals, and then maybe I'd be tempted to go store memory location A, then go recall A times recall A equals, and we've squared it. 384 should be my sample size. You might want to try that calculation, or you look it up in your textbook and have a crack. Make sure you're comfortable at getting that. Watch what happens if we don't want our error to be 5%. We'd rather it be, we only want to have an error rate of 2% perhaps. So this time we set it at 0.02, same sort of calculation, but now it's 2 times 0.02. We get 0.04 in the denominator, and when we square that, our sample size has to be much bigger, 2,401, if we want to be 2% sure with a 95%, or 2% error, within 2% error, and 95% confident. Sample size much bigger. The bigger the sample, the more confident we can be that it's a reliable estimate of the rest of the population. Let's leave it there for the moment. We'll come and do some more calculations when we get together in class. So looking forward to doing that with you. I've got to find, so I've just got to find where we are. There we are. And we'll see you soon.